Okay. Well, good morning, everybody, and welcome to our fourth Data Science Education webinar. This webinar is being made available through the Concord Consortium, a nonprofit educational technology laboratory based in Concord, Massachusetts, and Emeryville, California. We started these webinars because last February we convened over 100 thought leaders from organizations around the US and 6 continents in Berkeley, California, and our goal was to lay out the first steps in data science education. We are working to continue that momentum through our webinar series, and we're very passionate about these next steps in the revolution. You can learn more at our website, codap.concord.org. I'd like to introduce you to today's facilitator, Amelia McNamara of Smith College. Amelia is on the faculty of the Department of Statistics at Smith College and is a MassMutual faculty fellow. In this webinar, we'd like to talk about data science education and whether reasoning about variability is part of it. A recorded version of this webinar will be made available on YouTube. We will email you details about it through Eventbrite after the event. If you're comfortable sharing your name and face, please do turn on your web camera during the webinar event so we can see you. We like to see faces. I'd also like to emphasize that the format of this webinar is participatory by design. This means that we'll work together to decide the conversations, connections, and activities that we want to discuss. Bill will be facilitating the live questions that you have, and I will be the text-based questions on Zoom chat and Google Docs. And Amelia, you will explain what that means in just a few seconds. For those of you who are just joining us, welcome to our webinar. Our speaker is Amelia McNamara, who will be speaking about data science education and whether reasoning about variability is part of it. Okay, Amelia, I'll let you take it from here.
All right, thanks. So I do have some slides that I was going to present from. So maybe I'll try and figure out how to share my screen and get that going.
There are few enough of us that we could go around and people could say who they are.
Yeah, let's start with that. I was gonna talk first and then have people introduce themselves, but we can begin with introductions.
Okay, I'm Bill Finzer. I'm a senior scientist at Concord Consortium leading the CODAP project. And I know all of you. Jima?
Hi, I'm Jima Mojika. I'm a research associate here at the Friday Institute at NC State University, and I work on a couple of NSF-funded projects, one with Bill and Holly Lynn, and some other relating to stats.
And Rob?
I'm Rob Gould. I'm from UCLA Statistics.
And Elizabeth.
I'm Elizabeth Sylvan. I'm a senior research scientist at NextMap, and I work on the Open Data, Open Minds project, which gets kids and their teachers engaged in data literacy through paper circuitry.
So there are usually other people who come in later, and depending on what we're doing, we may stop for a moment and have them introduce themselves as well.
Yeah, sounds great. Well, I'm gonna see if I can share my screen. Let's see if this works.
You have succeeded.
I have succeeded. You can see some slides here.
Yep.
Okay, now I can't see you anymore, but I did put into the Google Doc a link to the slides and then a link to a Padlet that I think we'll probably use later as we start discussing things more. But the question that I want us to answer or try to answer today is reasoning about variability part of data science? And I've been thinking through these issues, and the way that I have been thinking about it is kind of like, what is data science? What kind of data are we working with as professionals, and what kinds of data might students be working with, and how does variability connect to the education of in data science and then in statistics. So like Talia said, I teach at Smith College. My appointment is actually in the program in statistical and data sciences. So I'm kind of always thinking about this distinction between statistics and data science. And I wanted to start with Venn diagrams, because somehow Venn diagrams and data science are intertwined. I'm guessing most of you have seen the one on the far left here. This is like the kind of ubiquitous Drew Conway data science Venn diagram, which says that data science is the intersection of hacking skills, math and statistics knowledge, and substantive expertise. I'm pretty sure that Rob has done a different version of this. I was looking for it and I couldn't come across it, but that doesn't have like the danger zone in there, which is maybe a little, I don't know, offensive or it is diminishing to people who work in that realm. And then I've seen recently, Hadley Wickham has been proposing this idea that data science is the intersection of data analysis and programming. And maybe we'll talk about whether we agree or disagree with that. And then when he put that Venn diagram on Twitter, then Sean Cross put up this sort of joke Venn diagram, which is whatever it is that you're doing, and then what data science is completely outside that circle, because it can feel kind of exclusionary. Some of these Venn diagrams don't include everything that we'd like to have included. But then when I think about data science, I'm also thinking about this kind of buzzword of big data. And there's a really classic piece that was on O'Reilly in 2012 about what big data means. And it supposedly has these characteristics of volume, velocity, and variety. And I've seen people add on a fourth one, which is veracity. So volume, it's too big to fit on one computer. You need to have distributed machines or some type of multiple processors to work on it. Velocity, meaning it's streaming in all the time, so you can't, you don't have a full data set to work with. It's always changing. And then variety, drawing attention to the fact that there's often different types of data, text data, images, really complicated timestamps, things like that. And I think I was considering this definition because it has the word variety, and I'm thinking about variability. But I think the variety in this big data definition is not about the kind of variability that we think about in statistics. And maybe that's one of the problems with this definition of big data. So then whenever I mention this definition of big data, I always reference Dana Boyd and Kate Crawford's sort of response to this, which is their critical questions for big data. And I think if we're doing data science education, we really want to be trying to underscore these ideas that big data is not necessarily objective. Data is not necessarily objective. Bigger data is not always better. You need context, you need contextual knowledge, otherwise it's going to be meaningless. Just because you can access it doesn't make it ethical. And then there's some access issues where if you don't have access to data or the skills to work with data, then you're creating these digital divides. And then sort of just like a final piece of this distinction maybe between like statistics and data science or big data. People often reference this paper by Leo Breiman of the two cultures of statistical modeling. And I think the paper actually goes deeper than this, but it usually gets connected to this idea that there's two different goals that you might have when you're doing statistical modeling. One is to have interpretable coefficients where a human can look at them and say, okay, I can understand what this relationship is in my data, and it makes sense that this coefficient would be positive, or this split point would happen here. And then there's another goal, which is more about predictive power. You don't care if you can interpret the model, you just want a black box that does great predictions. And so I think that connects in with this idea about variability. I'm just quoting from the GAZE report, the 2016 GAZE report. I think this is the college report, but the K through 12, I'm sure, has similar wording, which is saying that students need to be able to recognize and explain the central role of variability in the field of statistics. And then I think when I think about statistical variability, I think about this this kind of hierarchy, or this set of different ways of viewing data, which I'm quoting a paper by James Hammerman and Andy Rubin, but in turn they are quoting Cliff Knold, and this sort of these 4 different ways that you can think of data in terms of aggregate. So data as a pointer, data as a focus on the identity of individual cases, data as a classifier, and then this is where variability comes in, but data as an aggregate. So you have some data and you can see it as a whole, and you can describe variability in the data. So that's like one type of data that we want students to be able to reason about in statistics. And so then the question is reasoning about variability part of data science? And maybe I'll just pause there for a second and see if I can figure out how to unshare my screen. Oh, I'm not a Zoom expert. I'll pause share. Does that work? Stop share? Now everyone's bigger. So that's sort of where I'm coming from with this idea about variability and statistics and data science. And I just wanted to check in and see if anyone has first reactions to that question. Rob.
My question, I guess, is why would it not be? Other than the fact that it's missing the list of big data, I mean, what is your sense about why people might argue it's not?
Well, I've called out in my presentation some different types of variability, which we can talk about in turn. And I think that some of them, it's easy to see how reasoning about that type of variability would be part of data science. And some of them maybe like aren't relevant if you're doing data science or you're working with big data. We often talk about sample variability statistics, but in data science, maybe you don't have a sample, or have, like, not only it's not a sample, but it's everything. You have all of the data, and so where does variability come in?
We're thinking about data science education, and the part that students learning about variability should play. And I have the question, so we know what that's like in statistics education. How is it different if we're including data science? And I expect that that's where you're going. But
yeah. Maybe I'll try and put some of these questions in the Padlet, and people could do that as well. I have to admit, I'm not a Padlet expert. This is my first time making one. So one question was, why would...
We have one, or we have several new people who probably haven't found the Google Doc yet. So Talia, if you could rechat that. And the new folks, if you could follow that link, then you'll be in the Google Doc where you will find 4 links.
Yeah, so I should put the link somewhere where you could always see it. And so then this is like, how is variability in data science education different than variability in statistics education?
And when I follow the Padlet link, it seems to take me to the slideshow.
Ooh, maybe I put the links in incorrectly. Looks like I pasted in the same link twice, which does not work. So this, I believe, is the Padlet. And I will make that a link. Is that working now?
Yes.
Okay. At the top of the Padlet, I have, and I guess I could share my screen so people can see what I'm showing here. But at the top of the Padlet, I have the link to the Padlet and the link to the presentation slides. Then I dropped some links to like papers and other resources in here, and I'm hoping that as we're talking, you can include more references. Like this is something that I want to read more about, and so I'm hoping to sort of crowdsource a bibliography here. And then I'm just sort of throwing in some of these questions that people had. Okay, so maybe I'll just talk about the types of variability that I was thinking about when I was making this presentation. So I came up with these 5 types of variability, and maybe they're all kind of the same under the hood, or maybe there's some specific difference. But I came up with these, and I just had like some examples of each of them in here. So the first one that I was thinking about was variability within an attribute. So you have one variable and you're trying to summarize it in some way. It has variability that you could characterize. And again, this is that like sort of 4th point in the Knoll sort of hierarchy of different ways of thinking about a group of data. And so I have at the bottom some examples of ways that you might be able to visualize variability within one attribute, like using a box plot or using a dot plot, something like that. And I put the data from this onto the Padlet in case you want to play with it in your favorite statistical software. But I think it can be hard for statistics students to grasp the idea of variability even within an attribute. The other picture that I have here is the diagram that I'm currently drawing a lot for my students in my intro stats course, where we're talking about simple linear regression, and we're talking about the variability in some response variable, and then how much of that we can explain using a model. And it's been challenging for this group of students to get the idea of variability within an attribute, that you would care about something other than just the mean. And so then I guess the question is, if that's hard in a statistics class, then does it get harder if you're talking about data science education rather than statistics which focuses on variability? So that's one question. Is variability within an attribute part of data science education? And this one I think is. I don't know if anyone has wants to do a counterpoint on that. Why you wouldn't care about describing variability of a particular variable in data science?
Well, I suppose you could argue that looking at a single variable is rare in data science.
That's true.
You're interested in you have many variables. So I'm attempting to do the counterpoint, but
no, I like it. Thank you. Yeah. So I think that's. I have 2 thoughts about it. So one is, in this kind of statistics education with computers, where maybe Nick Horton and Randy Prime and Danny Kaplan say you should start with modeling and, engage with multivariate data sets in, as the first step. That seems like it's reaching toward data science, even if it's a statistics course using computers. And so they're agreeing with you that you should start thinking about many variables. And I think I agree with that, but I think that thinking about variability when you have more variables just makes it even more complicated to reason about. So with my example of the linear model, I've been talking to my students about the variability in the Y direction, and sort of talking about how we could visualize that in one dimension, like with a dot plot or a box plot or a histogram. But then when it gets sort of pulled out into 2 dimensions, they kind of lose that concept of variability in Y, and they're just looking at the sort of scatter of the whole scatter plot. And maybe that's okay, but to me it feels like adding more variables is complicating the understanding of variability.
I don't know if we need to raise our hands, if there's an electronic hand raise here. And so my thought on this, and stop me if this is not the direction you want to go right now, is that one difference between statistics education talking about variability as we know it now, and data science is often when you pull up a histogram or a box plot for a single variable in a big data set, those tools you just had on that last screen don't really help us get a grasp of the variability. I just saw you have the Oscar piracy data, and I think that's a good example.
Mm-hmm.
And just yesterday I was looking at fire department response times, where the right tail is so long that every picture you have is one big spike with a just long tail going off in the direction. So I think that's one way it differs, is that maybe it's important, but the tools that we've talked about aren't as helpful.
Yeah, that's great. I feel like I shouldn't be recording these things, because then it distracts me from.
No, don't worry about it. We're all doing things, so.
Yeah. But I think that's really true. I believe that this data came from James Molyneux at some point. So maybe this is some like Mobilize IDS.
It's not. I found it through Mark Hansen. And I think James found it through me.
Yeah. Okay. So it's UCLA affiliated data about movies and how quickly they get pirated, and sometimes things are getting pirated way before the movie is released, and then there's a big spike around when they are released, and some of them it takes a while for it to get pirated.
I should add, it's not collected by UCLA. It's from a journalist. Can't remember his name, but
That place? Okay, so good provenance. Yeah. So I mean, I think you're right that our traditional graphic tools start breaking down when you have really big, especially skewed. So now we're like other kind of mathematical, like maybe you want to take a log transform of that, but now you've got sort of like another mathematical idea that you're pulling into it. Or maybe we need some new visualization, like we shouldn't be using what Tukey was using to hand draw his data visualizations if we're going to reason about variability with large data sets. Other thoughts about that?
When you look at this piracy data, which I did pull down, what attribute would be useful to look at in terms of variability?
So I'll admit I uploaded it without having looked at all the variables. The one that I have here is about the difference between the screener release and the screener leak. But, you know, one of the variables that is probably in there is the box office gross. I should pull it up.
Well, I plotted US release to first leak, which has this negative number thing that you're talking about, positive number. It's an interesting distribution.
Do you have a link that you can share as well?
Yeah. I do.
And did you put a link somewhere?
I'll put a link in.
In the Zoom chat, Amelia.
Great.
I'll add to Google Doc too and in Padlet.
Okay.
I think also any of these questions that you bring up, we could spend the whole time on.
Yes. Yeah, that's one of the problems. Yeah, okay, so this data set doesn't have all the variables that I was thinking about. I think I have another one which is more generic movie data, which is a little larger, and then it has the gross box office, which is very skewed. So it has that quality that Rob's talking about, where maybe it doesn't make sense to use these tools.
I suppose another thing that happens in data science is the conflation of trying to clean the data and variability.
Yes.
Like skew distributions that Rob was talking about, that are not skew in reality, they're just skew because there's some weird data in there.
Okay. Yeah.
And how do we deal with that?
Yeah,
And,
I think
and
that's
and coming back to thinking about data science education, how do we deal with students working with such data?
Yeah. I think that's a type of variability that I had not considered, which is like, it's not real variability, it's errors or data transposition mistakes or something like that.
Yeah, it's not real variability, it's something else.
Right. Okay. So that was one thing that I had seen as a type of variability, which I do think connects to data science. Then the next one, I think, is maybe one where it might not connect to data science education. So this is this like idea of sample to sample variability. And again, I'm pulling stuff from the intro stats course that I'm teaching right now. This is a picture that I draw for my students on the board almost every day about, you know, we're trying to reason about the population, and all we have is the sample. Introductory statistics with randomization and session. And so then that sample to sample variability we often characterize by creating a sampling distribution, like calculating some statistic about the sample and then trying to say what the distribution of would look like under, you know, the null hypothesis or under some other hypothesis. And in my class, we talk about all these different ways that you could do it. We talk about randomization and simulation in particular. And I have this talk on YouTube where I sort of talk about doing randomization distributions for sampling distributions, and then looking at them and trying to reason about the variability, the sample-to-sample variability and how strange your observed statistic was. So I think that type of work is part of statistics. Doing that computational process of breaking a relationship and computing a statistic and doing that over and over again is part of statistics, even though it's very computational. And then the question is it part of data science? And so this brought to mind the AASA Data Fest, which I think many of you are familiar with. I know Rob is, because this is Rob's brainchild, but it's this weekend-long data hackathon for undergraduates that started at UCLA in 2011 and now has grown to be all over the country and across the world. We get a donor who donates some data, and students compete to try and find insight in the data. And I think you can see some of the past data sets here. Many times the data sponsors who donate data to us give a sample of, they pick 1 month of Ticketmaster data, or they randomly sample some number of people who went to the Edmonds.com website or something like that. It's not their full data set, but when these groups are working with data, they are not working with samples. Many of these are related to clicks on websites. I think we're trying to get away from that in DataFest, and maybe Rob can speak to that. But they're these sort of big sets that a lot of corporations are working with, and they're not necessarily samples. So the question is there sample-to-sample variability? And then I also want to bring back this quote from Boyd and Crawford that with big data, claims to objectivity and accuracy are misleading. So we have this big data set. It's not a sample, but it's also not representative of everyone because it's leaving people out. So maybe I'll leave that there for the moment. I don't know if I have a question here other than is there a way in which we should be bringing in this idea of sample-to-sample variability into data science education, or is that the break with statistics education? And maybe the answer is, again, that we don't have the right methods to deal with big data or new types of data. We need new graphical methods or statistical methods to deal with them. Yeah, Bill.
I have a question for Rob. Did you do a sample-to-sample variation in the Introduction to Data Science course for high school?
Is that right? Oh, he must be muted.
Yeah, Amelia might actually know this as well or better than I do. I don't think so. We do try to instill a sense of sample as something that's an incomplete record of something, but we don't about random sampling. I don't remember. I think we don't talk about random sampling.
Do randomization.
We do randomization. So yeah, that's right. We talk about it to that extent.
And I mean, we do kind of like randomization tests. I know there was something with cards where they write about themselves and then they shuffle them within the class and record some statistic and do that several times. So it's kind of a physical randomization test.
Right. I mean, so is that sample to sample value? I guess it is.
Yeah. I mean, I think the statistical problem comes in that you didn't have, your class wasn't a sample of something to begin with. It was the whole class.
Right.
And when you're randomizing, you're not really making a new sample.
Right. Right. Yeah, I'm on the fence with that one about whether that would be a necessary data science skill or not. I mean, my inclination is to agree with you, Amelia, that it's not necessarily part of data science as we usually think about it, although many, if not most, of the conceptual ideas behind it are really important, you know, for the reasons you were quoting about objectivity and all that sort of stuff. You know, where we've gone back to with the, of course, Andy Rubin and Katie Mucker's idea of informal inference, which is rather, and we've made it even more generous than they did. I think they defined it as something like a statement of uncertainty. You know, you're engaged in informal inferential reasoning when you've made a claim but given a statement of uncertainty in probabilistic terms. And I think we've kind of softened the probabilistic terms part, and would be really happy if just someone said, I see a trend, but I could be wrong. Because the data are incomplete, or because I only see a part of the time process, or something like that.
Mm-hmm.
So I think that's our notion of sample-to-sample variability in that class. Except, as Amelia is saying, is we do randomization tests, which I can't quite fit into that paradigm.
Yeah. Well, and the other thing that the informal inference reference was reminding me of is the making the call an insight with the box plots, the dancing box plots. That got an idea.
Yeah, but Bill, I guess I should add that it's called Introduction to Data Science, but it's very much a product of the California state standard. And so there were certain things that had to be in there in order to qualify as a math. And so I wouldn't say that it was necessarily it should be used as a standard for what we really thought an introduction to data science was, but as a good example of what data science could be within the California state educational system.
Good answer.
The other thing that is occurring to me is when I was preparing for this, I didn't go back and look at the Park City guidelines that's for college data science education, but Rob was there, I believe, and a number of other, my colleague Ben Baumer at Smith and a bunch of other people were there and came up with this document that describes what the ideal data science curriculum at the college level would look like. And I should have opened that up to see what they said about variability, because I would guess that there was some reference, but I don't know what was concluded.
I know there are a number of people who have joined us that are not necessarily aware of the various heads that you're putting forth. So please ask a question if there's something that's being said about IDS or DataFest that you want to know more about. Please chime in and ask a question.
Yeah, I don't think anyone new has joined with their video on, so I don't know if they want to introduce themselves or not, but if you'd like to introduce yourself, we'd love to hear who's here. I don't recognize all these names, I guess. Now I just have a black screen.
This is Dwight. I'm a new guy. Can you hear me?
Yes. Hi, Dwight.
Okay, hey there. I think I just stumbled across this on Twitter, and I'm a data scientist at Seattle Children's Hospital in Seattle, Washington. Mm-hmm. And The reason I joined on is because I have a great deal of trouble trying to explain to decision makers the difference between variability and point estimates. And so I was hoping to get some insights from you guys just by listening.
And what do you think what's the conceptual difference that your audience has as you try to explain this?
I don't know yet. I just know that I struggle mightily trying to get across the idea that the mean means nothing.
Yeah.
And it doesn't matter whether or not it's just like trying to explain a control chart or trying to work on a 600 variable predictive model. Either way, they just want they just want this point estimate, and trying to explain the variability issue is a huge struggle for me.
Dwight, I saw, by the way, thanks for speaking up. I was curious, you put in the Zoom channels, the variability, it kills you. Doesn't matter if you're trying to predict or trying to understand. Could you tell us a little bit more?
Yeah, this is, that came up when I'm talking to some other analysts in healthcare around the country. And another thing we struggle with is the difference between simulation as approach and straight up forecasting as an approach. And just this was a fellow data scientist at another healthcare center. His little comment is a variation that kills you. He thought this was the decision maker. The one kid in the emergency, the mean can't tell you anything about that, but that's the thing that kills you.
Mm. Great. Thank you. I also wanted to, we have another person who just joined us. Son, he's introducing himself. Hi, I'm a research scientist at Children's Health in Dallas.
I think, oh yeah.
I usually have the same issue with mean, and I use the illustration of a class average with overachievers and how skewed data can drive your mean.
Yeah, I think to some degree, explaining how the mean can be skewed is easier than explaining. So always, the average neighborhood, and Bill Gates moves in, and suddenly, you're all millionaires, but you're not actually. But yeah, like characterizing the variability of a distribution or of a model estimate or anything like that. It's really challenging. I think it's not intuitive. That's the problem with statistics, is that it's not intuitive, that you would need to care about something like that. It's kind of not a direct effect. I think people everywhere show it.
I remember meeting long ago a guy who was designing chairs, and he seemed to have this idea that if he fashioned the chair to fit the mean of people in all their physical characteristics, that he'd have the perfect chair.
I've heard some apocryphal story about designing cockpits in military jets. Yes. That were designed to be toward the average of everything, and it turned out that then no one was comfortable in the cockpit. Yeah. So, yeah, I think you can see why variability matters, but then like deeply understanding it is really hard.
But then it's not just that there's variability, but the shape of that variability matters as well.
Yeah. I have so many thoughts, but so we're
not going to get past variability. You might as well just give up.
My one thought, going back to the original premise, I guess, of how I understood this webinar, is that I think absolutely data scientists should understand variability, because we have to explain it to decision makers.
Yeah, I think you're right about that. I think it's important to understand. This is making me think of Amanda Cox did this amazing keynote at OpenVisConf this year, and what she was talking about was like uncertainty in the news. Probably I should have just had you all watch that instead of doing this webinar, because it's really lovely. I'll drop the link in on the Padlet. So this is Amanda Cox on uncertainty in the news. And maybe I'll just screen share and show you a couple highlights. I know the trick with screen sharing is sharing computer sound. Okay, so let's see if I can do this. Gotta try and find them. So she's talking about, like, if you remember those
sort of confidence interval-ish type things. And then we've got this needle that moves back and forth, and it stays in the middle 50% of the simulations. And it's using Perlin noise, which is the type of noise that's been used to make marble and clouds and fire. And Gregor Aish, my colleague, implemented that. And I think it's soft and graceful, but many people disagree.
So she's talking about their way of representing variability in the election results. She also talks about this great study about perceptions of probability.
I think that this is fun, because in some ways when I think about the Trump-Clinton odds, there's some work that says maybe it would be better if you always present those in terms of the adverse outcome. So we could, figure out whether our readers think an adverse outcome is Trump or Clinton, and then present it to them in that way, right? We could just like personalize it, or we could figure out whether you are the sort of person who thinks highly likely means 70%, and just like up that a little bit in our verbal descriptions of them.
So she's talking about this plot isn't coming through very well, but people they're assigned probability with these words like almost certainly, highly likely, very good chance, and there's actually a ton of variability in what people associate in terms of the assigned probability with those words. So sometimes we think that words are more precise than pictures, but actually they're also imprecise. And then she talks about, now I'm sort of jumping ahead to like modeling error. And I saw it for a second. She talks about the range of uncertainty for the budget deficit. Let me see if I can get her to actually tell you about this, because she's so funny.
I don't know. The classical one is this one. This is a government chart. Tomorrow, I think, will be an important day for the government and Federal Revenue Day, maybe, who knows. This is a chart that they release every time the federal government releases a budget. And I love it. I think it's one of the most delightful things, in part because if you know how to read the scale, this is like the depth of the Great Recession, and this is like better than it's ever been before. So essentially, this chart says like, I am pretty confident that it's not going to be like the Great Depression, right? Like 5 years from now. It's not even my favorite government uncertainty chart, though. That's probably this one, which comes from the economic report of the president in 2016. This is about how low the unemployment rate can go before it sparks inflation. And my favorite part, I mean, I think your laughter suggests you get it, but the footnote at the bottom, it says, a 50% band is used because increasingly higher levels of confidence produce confidence bands that approach unboundedness, right? And so it's like, it's even better than it even appears, and essentially that it says, like, I have no idea what this thing is anymore.
Okay, so you should really watch her whole keynote, because it's just lovely, and talking about like all these different ways that we represent uncertainty, using words and using numbers and using pictures, and it's just like hilarious like that. But I think that, I mean, looking at model uncertainty has really come to the point that times if you're reporting to a point estimate, and maybe it looks like, you know, inflation, but it could go down. So it's like anything is possible. We're really uncertain about this prediction. Okay, so, but that's sort of jumping ahead in terms of the, you know, I have these different types of variability that I wanted to talk about. The next one, I have to say, I don't have much to say about it. So, you know, the next one that I had thought about in terms of types of variability is measurement error and process variation, which is something that I almost never think about quantifying or describing, but I know both Bill and Cliff think about this, and I think I actually put an article, maybe it was by Cliff, into the Padlet. So my question is thinking about that type of variability part of data science? My argument would be no, but I want to hear, I don't think we have Cliff here today, but I want to hear what Bill has to say about measurement error, when it's important to think about and when it isn't necessary, or if it's part of this data science thing. On this, Bill.
Well, my daughter is starting a business in Kenya to help businesses think about their energy use. So she's helping them collect data. So those are measurements. And there's a process, like typically they're a manufacturer that's making something, they're consuming energy, and they're producing something. And they're looking at the relationship between those things. And the variability is where it's at for them. And I joked with her last night. I said, well, welcome to data science. And I would disagree with you that variability in measurement and process isn't part of what we would want learners to experience. I think dealing with that kind of variability is going to be so much a part of what many of them will encounter, either in their ensuing education or in the real world, that we would want them to see that.
Sorry, can you explain the context one more time? It's energy in Kenya.
Well, so we had a graph, which I won't share, but it was a particular business and the amount of electricity they were using for two different processes over a month or two. And there was a lot of variability, and there were spikes, and there were gaps, and so that's that other kind of variability. And how to make sense of that and how to make a recommendation and a call about whether they should change what they're doing, depended on how they interpret that variability. I'm making it sound like we did more analysis and understood things better than we did. We actually were just at the surface of this.
Yeah. So the paper that I put into the Padlet, this it was context for highlighting signal and noise, and I just pulled it up because I saw that the authors had called out three different contexts where you could have a process, noise, and signal. And so it was talking about measurement error, process variation, and individual differences. So, you know, that sort of individual differences part of it, I think, is what I usually think about, that, you know, the energy use from day to day, it varies because someone left the light on, when they left the bathroom instead of turning it off. And so, overall the energy use is about here, but there is some natural variability based on the process. So, but teasing out how measurement error or process error, which seems like it comes from a mechanical process, how that relates, that's what I don't understand and what I rarely
Hi, how are you?
Hello.
Rob, I see you have your hand raised.
So the electronic hand raise works. So now I'll lower my hand. When you say measurement error, it has a kind of precise technical meaning to a statistician, which often means, there's a repeated measurement setting where we're going to do multiple measurements of something. But I think, again, if you loosen that a little bit, it becomes a more important term. And I mean, I'm thinking of the Gapminder thing, which is often kind of cited as a great way of introducing students to big data and to data visualization, other things we associate with data science. But I remember when Hans Rosling presented at the ICOTS in Ljubljana that at least the people near me were really upset by the Gapminder because of its complete omission of the measurement error and the misleading impression it can give that data in the United States is known with exactly the same certainty as data in a country undergoing civil war. So I think those, as a critical lens, the notion of measurement error is a really important thing to instill in students. And again, back to our introduction to data science thing, it was something that the kids kind of picked up kind of naturally when they collected their own data, because they immediately become pretty skeptical of, it backfired on us, if you remember, Amelia. Instead of them thinking critically about the data and saying well, there's uncertainty here because I know I lied about my data because I was just too busy to be careful, they just kind of assume that everyone everywhere lies about their data all the time and that no data could be, so there's definitely, I think, a need kind of, at least that part of that concept to really be more precise about what we're thinking about.
Yeah.
When we teach it.
From that experience, I often call it the pit of despair. So you come in and you sort of feel neutral about statistics, and then we start teaching you some statistics, and you get excited about it. It's oh, data science can do anything. And then that point when you realize that there's fallibility, that's when you fall into the pit of despair. Statistics is meaningless. We can't do anything. Everyone's just lying all the time. So the challenge is coming back up out to some neutral place. And I think that's the challenge. I don't have a magic way to do that. Yeah. But in terms of the Gapminder example, I'm interested to sort of think through that, because how could it have been better represented? Some uncertainty bar around each of the points or the traces, or I don't think that we have a good way of, again, representing or characterizing that, of drawing it through systems that we have currently. Yeah, I'm not sure.
It reminds me of how you started with univariate. And because it's simpler, because you have a chance, perhaps, to understand what's going on in the univariate situation. And in the Gapminder talks that Hans Rosling did, he's very far from that. He's 3 or 4 variables all at once. And you're not going to be able to bring in measurement error in that context without cluttering things up so much that people can't see his point.
Right.
So you have to go back to something simpler and just look at measurement error comparing the United States to Swaziland. But that's going to take too much of his talk time, and we're not going to be excited anymore.
Mm-hmm.
And Rob is nodding his head like, yeah. But are we doing a disservice, I suppose, is the question. Is Hans Rosling doing a disservice to his audience by neglecting it? And I'm not sure he is.
Well, yeah, well, and I guess in fairness, I mean, we can't expect everyone to do all things.
Mm-hmm.
But I think I would say if I were using Gapminder in a classroom context, I mean, lesson number 1 would be the Hans Rosling version presentation, and maybe lessons number 2 and 3 as well. And lesson number 4 would be, well, where did this data come from? And which values do we trust more than others, and how does that change our conclusions?
Yeah.
Yeah.
But
So that's back to those, like the critical questioning of the data.
yeah.
And again, I think that that's an important skill for students to have, to be able to sort of look at some output and problematize it and sort of talk about what the drawbacks are. But I think there's like more space to quantify that better, or to visualize it, and not just sort of, it feels like falling into the pit of despair again. Like, well, I did this thing, but I can't really do any better about quantifying or controlling for the measurement error. So I'm just going to add a little asterisk caveat that maybe we shouldn't trust these results because there might be different variability.
Well, so Amelia, I was going to ask you, I mean, the other part of this was process variation. And you mentioned like click-through data as a type of, do you see that as a process? I mean, do you see reasoning about that as requiring process variation?
I do. Yeah, I was thinking about that data example along with process variation. And I think there's a place for it. Although I think that weblog data has different types of maybe errors or missingness or messiness than other types of data. Hillary Parker talks about this on the Not So Standard Deviations podcast a lot, because she had worked for Etsy for a long while, and now she works for Stitch Fix. So she's like a data scientist at scale at a corporation, and she works with this like weblog data, or they'll do A/B testing. And she says that the data that you get is very clean in a certain way, because it, unless something went horribly wrong with your server, you have the timestamp and the click and their IP address, and it's complete in a certain way. So it's, because it's machine generated, you're not going to be missing some of the variables like at random or because of some pattern. But I think there is some evidence of the machine, the process in the data, which maybe you care about. And certainly there's these larger questions that surround it.
What do we mean by process variation?
So I should just take a screenshot of this and put it in the Padlet. Where did I find it? What is this? Can I just drag it on here? I remember there was some discussion of this. I was thinking about it. I don't know if it's actually going to work though.
There it is.
Yeah. So this is from that paper that I have in my list of papers, where Cliff and Anthony are talking about these different contexts. That, there's repeated measurements that generate measurement error. There's manufactured objects which have process variation, and then natural objects that have individual differences. So, what the process variation might be, I don't know, in the weblog data. The manufactured data that I think about a lot is Fitbit data, because I keep track of my steps. And of course, it's an object which is tracking some accelerometer and altimeter data, and trying to decide if I've taken a step. So the actual data must be some continuous signal, and then the algorithm is making a choice about what is a step, and maybe there's some process variation in there, in the translation of that continuous signal to the step. I don't know.
Well, I think you might also, at a higher level, you might say the process variation is the variation that you see in your day step count, or you're summarizing that.
That's
right?
not individual differences from natural objects. I don't know. We need Cliff here.
Yeah, I'm not sure. I was thinking of individual differences to be how my step rate differed from yours.
Yeah.
So I was thinking of processes too in terms of sensor data and things along those lines, and so it falls in that category. And then the clickstream example, part of the act is to try and hypothesize what a pattern for a person looked like as they meandered through a website, and then see what the trend was of lots of people. So it was kind of both person-to-person variation, but also the within-person variation.
Mm-hmm.
And it's the within-person variation, I guess I'm thinking of as process variation. But
okay.
I'm not so sure.
Yeah. Yeah, I think I sort of glossed over that, the difference between individual variation and then the individual to individual variation. Maybe both of those are variability within an attribute, I think is what I put on my slide, but there's it's more granular than that. Okay, let's see what so then I'll present again for just a second. I can figure out how to do it. So the next type of variability that I was thinking about is modeling error. And so I have my picture again that I've been showing to my students about, we have some data, it has some variability in the response or the Y variable. We're trying to explain that variability using a line. And then, we've been talking about R squared as a statistic that's characterizing what % of that variability we were able to explain. And so the conceptual challenge for students here, I think, is that they often say, well, if it's 0.68 R squared, we're correctly predicting 68% of points. But it's not actually that we're correctly predicting 68% of points. We're probably not correctly predicting any of the points. But of the variability that we saw initially, we've managed to, reduce the variability by using the model as an explanatory tool rather than just the mean. So that's yet another type of variability, I think. And then I was watching Rob's webinar from the last Concord Consortium webinar, and now I'm putting Rob on the spot, but he said he was going to look for the real values of the data, because you were trying to predict what sport someone played from some data about their age and weight, something like that. And I liked that model because it didn't have a numeric response. It was a classification problem. And so then like deciding how good your model is and how much variability there are, that's like sort of another task. And I think that is a data science task. So I don't know. Did you find the real data, Rob? Or was that an empty promise?
That was an empty promise. I'm not sure it exists anymore. It is real data, but I don't know if I had the records to find it.
Yeah. So I think you were trying to predict like if someone played soccer or football.
Yes.
Was it just the two? Okay. So when you have a classification problem like that, maybe you want to make some type of confusion matrix and see how many you got right in each category out of all of them.
Right. Well, and I think, so if data science is prediction, and one of the thoughts I'm still wrestling with is, how do I know when I'm talking about data science, and how do I know when I'm talking about statistics education?
Mm-hmm.
But I've always had a hard time motivating measurements of variability and regression. Like, I guess I can tell students that the standard deviation is useful because of the empirical rule or something. But then when you get to R squared and that kind of arcane meaning, it's hard until you start to say, look, this is an indicator of how good a job you're going to be able to do making predictions.
Mm-hmm.
And then, someone asks like, well, why don't we just measure how far off our predictions are? And that's kind of what R squared is doing. I mean, it just makes more sense to think of it. And in that sense, I think this is like a really strong data science sort of thing that people should be learning if they're learning data science. And something that I think we often don't teach, like we don't often say to students, predict the weather for that next 10 days and tell us how good a job you did. Mm-hmm. And force them to kind of come up with their own measures or something like that.
Yeah.
I mean, this is still an area I think we present very much from a mathematical paradigm.
Yeah.
These were the loss functions that history has given to us, and if you crank the calculus map here are the models that come out of the loss functions, and don't go too much further about the common sense behind it. So.
Yeah. So is your conclusion that we should talk about R squared, but only as a measure of how good our model is, and talk less about the variability?
Well, I guess my conclusion was I'm interpreting modeling error in this context, in a data science context, to be prediction error.
Yeah.
And that's what we should be focused on.
Yeah. Oh, yeah. So now, again, I've collapsed two things. Oftentimes we have some standard error on our model terms. We've quantified our uncertainty about the model, and that's different than the predictive errors, which are another type of variability or uncertainty or something. Yeah.
Well, I think I came into this believing that in data science, there's a different variability is a different phenomenon. And now I'm thinking, well, maybe it's actually all statistics. We have one or two data scientists with us wonder if you have a comment about that. Our medical person who deals with doctors, for example.
I missed the exact question, sorry.
So, as a data scientist, do you find yourself dealing with variability in a different way, qualitatively different way than a statistician would when you're working with your clients? Or are you facing the same dilemma about how to explain this that a statistical consultant would?
To me, I feel they're the same.
Uh-huh.
Yeah, I think you can see my bias here, which is that, you know, if we think that data science is some intersection of programming and statistics and domain knowledge, that part of what's coming from statistics is the importance of considering variability.
Yeah, to phrase it, go ahead.
No, go ahead.
I was going to say, to phrase it in a different way, I won't hire anyone who is just good at machine learning. They have to have some stats background.
Mm-hmm.
Yeah, and maybe that's connecting back to that sort of two cultures idea, the Bryman paper of, just doing the best possible or more understanding of the underlying process.
Bill, can you say more about the moment thought variability was different for data science?
I don't think I can anymore. No.
Our other participant, who's a data scientist, agrees that they are the same, for what it's worth.
Oh, thank you.
Yeah, I think one of the complaints from statisticians and the science crop up that are computer scientists is that the treatment of variability is not as in-depth as we statisticians get to be in data science. So to me, that's the main contribution there.
Okay, wait, explain why I thought. Because in statistics education, the data sets that we deal with have been sanitized. And we have variability that's easy to understand, and we don't have to dig to see the variability and clarify what kind of variability we're talking about. But but data scientists face unsanitized data, big clouds of data, and getting to see the variability. So I guess it's not the variability itself, but the process of getting it into a form where you can actually talk about the variability. That's something we would deal with, certainly in statistics education, and speak to this, would more expect the class to have already mapped, and just to be able to tell them about the we can see. My perspective came from.
Yeah, it makes me think of how statistics textbooks often use these sort of contrived examples where they'll say, like, here's a small data set and we want you to make inference, and by the way, we know that the standard error is 2.4, and so now that you know that, you can answer this question, or you know that the population standard deviation is this particular value, which is not something that you would ever know in real life. And that I think statistics education has been moving to be much more like data education, more real life and trying to bring you into these scenarios where you don't know anything about the population. You have to make all your inference from what you have on hand, and I think that we're moving closer to science education. So I just had one type of variability that I had kind of identified a priori, which is kind of my pet favorite type of variability right now, and maybe it's the most data science-y. We'll see. I'm going to share my screen, and I don't think my videos are going to work, so we might have to do something else, but maybe I'll have you do an activity before we do that. Okay, so so this is kind of my list variability I had identified, which is the variability in your data product, whatever you come up with at the end, due to parameter choices that you made in your analysis. So the one that I've been thinking about a lot recently is how different your distribution can look when you make a histogram based on how you decide to bin the data. So here I have that same screener release to screener leak data, and I'm looking at the distribution with these pretty wide bins. I think they're maybe 50 days wide-ish. And then over here, it's more like 15 days wide, and you can see different characteristics of the distribution. Here, I think I've left the bin width the same as it was here, but I've shifted it over a tiny bit so that you can see that spike right at 0 a little bit more clearly, or right after 0. So that's one place where your parameter choice makes a difference in terms of what you get at the end, and there's some variability there. This is my other favorite example. Let's see. I don't know if I chose the right kind of screen sharing so that you can still see this.
We can still see it.
Okay. This is some work by Nick Diakopoulos and Stephen Cass, who I don't know, but it's a ranking that Lee asked them, saying like in 2019, what's the top programming language? And it's Python, C, Java, C++, C#, and then R. And what I like about this is it lets you look at the IEEE spectrum, their favorite rank versus the trending, and you could add a comparison, so the difference between the trending ranking and the spec ranking. So the spec, so it's swap and moves down a little bit, something like that. And then he also allows you to make your own custom ranking, where you can edit how the ranking is generated. So you can say, I care more about the Stack Overflow questions. I care less about GitHub. I care more about Google Search. I care less about IEEE Explorer. And then you can see how that changes the ranking. It's sort of moving Python down a little bit, and again moving C up. So he's making it explicit what the parameters in the ranking are, and then he's giving you access to see how things vary when you change those. So I had some examples in a couple different languages. Oh, maybe it's working. And we could maybe, if you had a pet favorite piece of software, we could look at how this works. But so for this histogram example, if you were working in R and ggplot2 and you wanted to see how the bin width that you had chosen impacted the distribution you were creating, you would have to write some code and then hit the up arrow and edit the parameter and hit enter and look at the results and then do that again. And you have to sort of hold this all in your mind to make the connection between how your bin width changing and your picture changing were connected. So in sort of the Brett Victor inventing on principle scenario, that's a bad thing to have to do, to have to hold those states in your mind. If you're using R and you want a little bit more direct manipulation, there's a package called Manipulate. And if you use that, then you can generate a little slider, which will allow you to slide around, and then you don't have to write any code, and it's easier. You're doing more direct manipulation than you were just using ggplot2, because you can move back and forth, but you still have to drop that little pointer before you can see the updated histogram. It doesn't update automatically as you're moving it. And then I think my next one was Tableau. So this is a data visualization platform that people often like because it's a graphical user interface, but it makes it very difficult to adjust parameters in a direct way. So you can see I'm like sort of going through all these menus, and I've created a number, and then I can make it a slider, and that sort of allows me to make these comparisons between the different types, the different bin widths, and sort of step through them. But I think this is much less than ideal. It's not really a histogram either, because the bins are not continuous. They're not connected together. And then I think maybe the most successful, here's Fathom. So you can make a histogram of some attribute, make a dot plot and then aggregate things together. So you're going from that pointer to aggregate. And then you can just grab the bars and adjust the bin width to see what the distribution looks like with these different parameter choices.
Can I do another example?
Yes, please. Is it going to be CodeApp?
Yes. Are you doing CodeApp next?
No, I'm not a CodeApp expert, and I'm trying to figure out how to even stop sharing my screen so that you can hopefully share. Stop share. There we go.
Oh, I might have just left.
You left?
Yeah, I think I just left. Go on, I'll come back.
Okay. So to me, that like studying that kind of variability or thinking about it and being aware of it is not something that has been very emphasized in statistics education. Again, maybe because of this history of doing things by hand, and we're sort of slowly moving to be more and more computational. But I think it's an important thing to reason about, and it is a way in which your results can vary pretty extremely.
Bill, once you're done, Rob also says to Amelia, what about your own demo that shows histogram variation?
Oh, yeah.
Yeah, I have this explorable essay, which I could also show. Maybe I'll do that now while...
Well, I got it now.
Got it. Okay, great.
Yeah. So here's the screener data,
Mm-hmm.
and a not a histogram, but still a distribution. And I think it's interesting to just see the effect of the point size, which is used for the binning.
Yes.
So if I make the points very small, I see that.
Mm-hmm.
Like I can see all the detail. And then as I make them bigger, I get this interesting effect that's similar to the histogram, to the large bin histogram.
Yeah.
That's all.
Okay. Well, maybe I'll share my screen again. Let's see. In my presentation, I have some GIFs of how this essay works, but I'll actually go through the essay a little bit with you. So this is some work that I did with my collaborator, Aaron Lunzer, and he and I thought about histograms for a really, really long time, but we're still in process working on this. So if you have suggestions, I'd love to hear them. But we sort of were using that same hierarchy from the data as a pointer, data as a case. I'm forgetting all of the, there's those 4 levels. But so we start with some data, which is just an unordered pile of values. Like you have some numbers and there's nothing, you've done nothing with them. And then the first step that we do is we order the numbers from largest to smallest, which gives you some idea of the distribution, but of course it makes it seem like the difference between 10.5 and 13.3 is the same as the difference between 15.3 and 15.5, because they're just right next to each other. So the next thing we do is draw a number line and then drop all those data points down onto the number line, sort of like dots. And then we show if you have a different data set, that first one didn't have any repeated values. This one is age and years for NBA athletes, and so the data, it's by year, their age. So there's a lot of repeated values, but it's almost discretized. There's only a few possibilities because we're not doing half years. And then this is some data about the number of seconds between eruptions of Old Faithful. And so you can see there's still some repeated numbers, but the data is a lot more continuous. So it's piling up where there's exact repeats, and then the rest of them are just right along the baseline. So the first thought that I had in terms of Bill's demo with CodeApp is when we were working on this, we found, he and I iterated through tons and tons of data, and any repeat would have this value, but it would be 100 times or 200 times. And so the stack of dots would get extremely tall, and it made it hard for us to have that visualization because it was sort of like going off the top of the chart. So we played with the idea of, well, what if a dot represented 10 eruptions? But that sort of gets away from the pointer to an individual. And then we also played with what I think CodeApp is doing, where you have, it's the exact same value, but you sort of jitter it a little bit or kind of overlay, and you rely on the sort of visual density to show you that there's a lot going on there. But we ended up just using a data set that had few enough repeated values that we could show them all as individuals and stacked up in this particular way. I think maybe later in the essay we had to do something else. But then we show how a histogram is really just kind of counting up how many of those values fall into each of these bins. And another design choice that we made was we didn't want it to seem like it was an ordered process. So we didn't want the balls to fall from left to right or right to left. So every time you run this, it picks a different random order to drop into the bins, so that you can see that it's sort of, it like kind of happens all at once. We want you to be able to watch the process of aggregating up. And then, of course, we make it possible to vary the bin offset and look at the distribution there, to vary the bin width and look at that distribution. And then we have these more complicated areas where you can play with the bin width to compare distributions. If you're gonna vary the bin width and compare distributions, when it has a really small bin width, they usually are little short bins because they're only capturing a few of the dots. And when they're wide bins, they get taller because they just naturally are able to grab more points. So it's easier to make comparisons if you plot as densities. So then you can kind of see how they compare. Densities are really hard to like think about or explain to people. Rob is nodding a little bit again, because they're a little bit subtle. It's sort of about how extreme is this bin. If you thought that there was going to be a uniform distribution that had the same area, is this very dense or not as dense as you would expect? But it does allow you to compare between data sets of different sizes.
So I love this. So you are varying something in each of these examples. So
yeah.
A kind of variability.
Mm-hmm.
The variability in the choice of parameter.
It's true.
Which generates another kind of variability, which is the variability of the presentation or the result. So, and am I right that what you want to get across is that when you look at a histogram, you're looking at one histogram of a space of histograms that could have been chosen. So
yes.
Just like the mean is just one number, this histogram, it could be different.
Yes, absolutely. Yeah, I think that if you have a type of tool that generates some default, it's easy to just keep that default and think that that's some type of true representation of your data. When, I'm not doing anything about sample to sample variability here. I guess I'm modeling in that I'm binning the data in some way. So it's sort of like modeling variability, but it's really just like presentation variability, and it gives me these different stories. And you're absolutely right that as we go through the essay, we're trying to kind of build up people's intuition. So first we only let you vary the bin offset, then we only let you vary the bin width. Then here I'm allowing you to make a sweep. So it might not be coming through very well, but you can go and try this. If you click the green square in the essay, it overlays a bunch of transparent histograms. So these all have the same bin offset, but slightly different bin widths. So you can see sort of like a cloud, a bunch of different histograms. And then I think the next step allows you to do the same thing. I could pick a bin width, and then I can do a sweep on bin offset. So these are all histograms with the same width, but slightly different offsets. And then I can sort of, it's almost like a kernel density. I can see the shape of the data by looking at a variety of different histograms.
But what is, for this particular data set,
mm-hmm.
Why have a histogram at all? You've got the dots up there. Those are the actual data.
Yeah, well, I think because, and maybe this relates to like measurement error or process error, we might think that the difference between 301 seconds and 302 seconds, we don't actually care about it that much. We happen to have observed, 2 301 and 302 seconds, but that's really, just, a couple minutes, and so we're interested in kind of binning the data. And then I think the case that I'm talking about, which obviously didn't come through because we didn't make it work in the essay, is that when you have really big data, if you had 500 repeated values here, you couldn't show it as dots. The dots are just going to be like off the scale, like Rob was talking about with it's sort of like the opposite of a long tail. It's like a tall spike.
Well, actually, what we do in both Fathom and Kodak is we don't let it go off the top. We overlap the points so that you're always seeing all the data,
Yeah.
but it's overlapped a lot.
Yeah. So I think, that's another design decision.
Yeah.
So that there's some variability there. We talk about bin openness. And then I think our final word is that we want you to be able to vary both the offset and the bin width. And, you should be able to see the relationship between varying those two parameters together.
Yeah.
But like you were saying before, Bill, this is somewhat easy to think about because it's a univariate case. And even in this univariate case, there's all this complexity to how your parameter choices impact what you see. And then the world of data science is so much more complex. I have another example that I often do about cut points in regression, which might be a decision that you make very early on in your analysis, and then you move on and you never think again about how that choice impacted your final results. So like this is like maybe not unique data science, but it should be part of data science, is thinking about the consequences of your parameter choices in your analysis, and that's like a form of variability.
And I like that you're not bringing in the trope of how to lie with statistics. It's that you can get a great many different presentations depending on your parameter choices.
Yeah, I have had people who've seen this say like, well, this is just going to be a tool for people to cherry pick the story that they want to see. And, I think to some degree maybe that's true, but all tools can be used for good or for bad. And so we're trying to, as educators, I think we want people to understand the range of possibilities, and we're hoping that they're going to go and use those skills for good.
Well, so I raise my hand and I'm calling on myself. As this discussion goes forward, I mean, the line between data science and statistics education is getting blurrier for me, and it was pretty blurry to begin with, I'll acknowledge. The other thought that comes into mind in looking at this is how this tool builds such a nice bridge between the sample data, in which case Bill is saying, why not just stick with the dot plots, and the notion of a density, where we're kind of backing up a long ways and saying, if there were more NBA players, or I don't know, I've forgotten what the data were exactly, but if things came out differently, good model drive that difference. So trying to smooth it into a mathematical modeling approach, which I see as firmly in the camp of statistics. But I agree with you, this notion of worrying about and thinking about how parameter choice changes, how legitimate parameter choice changes can affect the story that comes out, needs to be told as well.
Yeah.
I mean, I'm thinking too, my pet peeve when we teach, when so many students now see maps of statistical graphics, they don't see the variability of them. They see pinpoints. So, I mean, like yesterday, I was trying to find about fire example.
Mm-hmm.
All I could find were little icons of flames as points around the state, and nothing that communicated to me where the current flames were, where they were moving to, any sort of projection. And the same thing comes to most maps, the points of where crime have to see that smooth, mm-hmm. to get a sense of, and then once you begin to smooth, you also want to see something like you're trying to communicate, Amelia, which is that what happens if I change the smoothing parameters? What's the global picture of this model? So I think this is a really promising direction to be exploring.
Are you trying to set me up for my smooth map demo?
I'm not trying to, but that's great. Take it away.
I'll just show this. Aaron and I worked on this as well, and it's much less fully fleshed out. But this is a map, and it lets you change binning in 2 dimensions. So maybe you are interested in, let's see, sort of big. This is not exact.
What data?
So the data is kind of stupid. This is locations of earthquakes in Southern California, and there's just a dot for every earthquake over a certain size. So in this case, maybe you do want to look at the points, but it was just point data that I had easy access to. And again, I'm just showing like the binning is a form of smoothing. I'm not even doing like a smoothing. I'm just binning. But then you can see how just adjusting. Here I can make this whole area kind of dark, or I could split it and make it all kind of lighter. So we're thinking about how to make this more clear, and thinking about this as a 2-dimensional extension of that histogram work. But again, when you get into more dimensions of data, then it becomes more complex to show. Like I want to show several side by side or over the top of one another, and it gets much muddier in the visualization if you do that. So we need some other uncertainty quantification maybe.
Very nice.
Yeah, so I think the last slide that I had was just asking if there were other forms of variability that I missed when I was thinking about this, because I had those, maybe I can share.
Amelia, before we go there, there's a question posted. What about making that histogram app using predictive model output, for example, with some random walk simulation results, then linked to it, what he just mentioned in terms of modifying parameters? Maybe that was for you, Rob?
Yeah, so I think, I'm not sure I understand the entire thing, but some distribution of it made from a random some model. You might have some variability in your predictions or model coefficients from a number of different simulations. And then I think that's the sort of like thinking even bigger that I'm saying is everywhere that you make a choice about a parameter in your analysis, you are increasing the space of possibilities of the outcome, and trying to make it easy to see how those choices trickle down is something that I think we need to put more emphasis on.
Mm-hmm. Great.
So as you're making a presentation, all parameters should vary. They should all be wiggling.
Maybe, yeah. but again, I think, we were talking about even trying to tease out the, natural variation versus measurement error, like if you have just two types of uncertainty and you're trying to characterize both of them, or if you have, three things being plotted, once you get into these higher dimensional spaces, it's harder to conceptualize. So I think we need better tools or something.
Better human minds.
Yeah. Well, I don't know. I think we've kind of come to an asymptotic human mind state. So I think we need tools to help us be more powerful. Yeah. So.
Well, we're coming to the end.
We are. Yeah. So I think, I had laid out these 5 types of variability, and it was sort of like we talked about within individual and between individual. One thing, this was process error. Bill brought up the variability that isn't, so errors in data that make it look variable. Modeling error, we kind of talked about uncertainty of model parameters and errors in modeling predictions. And there were probably some more things, but those, so I thought of some more types of variability. And if you think of even more, I'd love to add them to my list. But that was all I had thought of and all I had to say.
Well, I think this was a fascinating discussion. And thank you very much. And thank you all to the participants that came to this webinar. And you can tell your friends and colleagues that there will shortly be a recording of this posted, and you'll get an email about where.
Yes.
So I think that's it.
Fantastic. And we hope to see you all at our next webinar with Michelle Wilkerson on November 7th. We'll be sending out emails with details about that too.
And what will she be talking about? Do we know?
To be determined, she said.
Okay. But she's a researcher in data science education. And I think understanding how people think about data is what a lot of her research is about. All right.
Yeah, thanks so much.
Thank you. Thank you.
Take care.